Today's lecture is one of two parts concerning organometallic reactions in synthesis. These are organic compounds incorporating carbon-metal bonds, and they are called organometallic compounds. And in this lecture, we'll cover the general characteristics of the carbon-metal bond. We'll be looking at preparations, characteristic limitations, and uses of Grignards, and also Gillman reagents. We'll be also a few examples of courthouse coupling and the Simmons Smith cyclopropanation. In the next lecture, we'll be then looking at palladium promoted couplings, i.e. the Still, Suzuki, Negishi, Heck, and so on, and also a focus on olefin metathesis. Common types of organometallics are Grignards and organolithium reagents, although there are a variety of others that has copper, cadmium, zinc, mercury, etc. Typically, an alkyl lithium, you can react an alkyl halide with lithium metal to generate that lithium species. And the same thing with Grignard. You can react the alkyl halide with magnesium, and that will generate your Grignard reagent. Notice that in an alkyl halide, you have an electrophilic carbon because of the polarity pointing in this direction, i.e. a more electronegative halide. However, on reaction with the metal, then the organometallic has the polarity in the other direction, i.e. we can now represent the species as a carbon and ion. So from an electrophilic site to a nucleophilic site. Reactivity of organometallic compounds depends on the reduction potential of the metal. This parallels the ionic character of the carbon-metal bond. Notice that when we're looking at electronegative values, for example, you can see there's an increase from lithium, zinc, all the way to carbon. Now, if we compare, for example, a carbon-metal bond, which is lithium-carbon, you can see there's a difference of 1.5. It tells us that this lithium-carbon bond is more polar than the copper-carbon because the difference in the copper-carbon is 0.6. It means that the lithiated species is more reactive than the copper species. The organolithium compound can be prepared by using the organohalide with lithium metal in a suitable solvent such as hexane or diethyl ether. These are all nonpolar species. We react the alkyl halide with the metal to realize the lithiated species, which is quite nucleophilic at that carbon center, which we can represent as a carbon anion. Under the same conditions, when we do react the alkyl halide with magnesium metal, then we realize the Grignard reagent. Note carefully that the magnesium is 2+, the halide is -1, realizing a -1 charge on the R group. So therefore, this R group, which is now nucleophilic, we can use this nucleophilic species to attack an electrophile, realizing a coupling, i.e. for example, a carbon-carbon bond. For the Grignard reagent, the most common carbon-carbon coupling application is with carbonyl compounds. The Lewis acidity of the magnesium center is responsible for the reactivity, coordination with the substrate via the oxygen, increasing the bond polarity in the carbonyl and facilitates the transfer of the carbon ion fragment to the carbon center of the carbonyl, realizing this species which we then quench out to generate our product. The normal representation of this mechanism is we simply just have the R group here as an anion representing our Grignard, attacking our electrophilic carbon center to realize an alkoxide, which we can then quench with a proton, whether it's from an acid or from water, to generate, in this case, an alcohol. Organolithium and organomagnesium contain carbon anions, which are very strong bases. Therefore, they react with acidic centers in a reaction mixture. This is the limitation to their utility. For example, you can see here, I have the general equation where I have a Grignard in the presence of water, and then the Grignard dies. See here, for example, I have an alkane, alkyl halide, reacting to give it a Grignard, and you end up with the alkane that's missing a few carbons. Here you can see we can generate the Grignard, react it with deuterium oxide, and realize the deuterated species. The same thing with the lithiated species. Here you can see we generated benzene from this aryl halide. Here, of course, we have an alyl halide. We end up with the alkene. Actually, herein, you can see that we have a good method to generate deuterated hydrocarbons. Let's think of this in an acid-base context, because as we stated, these are easily quenched by even very weak acids, i.e. water, alcohols, etc. A quick review of the pKa of various groups indicate their susceptibility to basic attack by these carbon anions. You can see that the Grignard itself is a species that was generated from a conjugate acid with a pKa of 50. So of course, when it comes across a more acidic species, this Grignard will be quenched. The same thing when it comes across the amines, which have lower pKa than the conjugate acid of the Grignard. When we look at the pKa of acidic centers, these electrophilic species such as carbonyls and the nitros, you can see that pKa range is also a lot less than the 50 of these carbon anions. Hence, these will also react with our Grignard center. For this reason, we cannot make Grignards or organolithiums with acidic or electrophilic functional groups present in the molecule. Acidic protons and electrophilic centers will kill our reagents and won't allow them to be generated in the first place. For this reason, we can employ protection techniques before main reaction sequences. And this will come up in another one of our lectures later on. Of course, they make great nucleophiles and add efficiently to electrophilic carbons, such as here we got a 2-carbon coupling with oxide. We can also have Here, carbon dioxide reacting to give us a carboxylate. Herein, we can see a ketone reacting to give us a tertiary alcohol. The mechanism that we saw earlier, we can just think about this epoxide, which is asymmetrical, and the nucleophilic center, of course, is your Grignard, and the electrophilic center is the least substituted carbon on the epoxide, and so the reaction will occur by simply attacking that center to realize this alkoxide, which we can then protonate to give us our product. This is a 2-carbon coupling, and the reactivity of the epoxide is due to ring strain, which increases the electrophilicity of that species. So we could ask ourselves this simple question: what is the product of this reaction? And quite simply, we know that it's a coupling reaction between the Grignard and a carbon on the epoxide. And so we can simply number our carbon 1, 2. Let's represent that by this ethyl moiety. And that will attack our epoxide. Our ring will open up. And let's call that 3 and 4. So there's coupling between 1 and 2, carbon 1 and carbon 3. There's that oxide on carbon 4, which will quench. So if you notice, that's going to be a 1, 2, 3, 4 carbon primary alcohol, which gives your answer as D. That these carbon and ions are quite good nucleophiles that can react with any electrophilic carbon center that they come across. And for example, we know that ketones will react to give tertiary alcohols, and esters will react to give tertiary alcohols also. We already saw where the carbon dioxide react to give acids. So as a nucleophile, we got a wealth of electrophiles that we can react with to generate various products in organic chemistry. The Gillman reagent is terribly important. It's formed using the alkyl lithium reagent with copper 1 iodide. A transmetallation reaction occurred, i.e., an alkyl group is transferred from the lithium, or the copper, which is more electronegative. This electronegative difference between lithium carbon compared to copper carbon, i.e., a less polar carbon metal bond, means that the Gillman is a much milder carbon and ion than the Grignard or the organolithiates. Note that the species, we have 2 moles of R group associated with 1 copper, but only 1 mole is available to us for organic synthesis because of the resulting insoluble alkyl copper moiety that occurs in the reaction mixture. Coupling reaction that occurs is the Gillman reagent with an alkyl halide. And in this case, you can see that we have here a methyl species reacting with alkyl halide, and we literally replace both halides. Herein, you can see that we reacted the Gillmans with our vinyl halide, and we retained our stereochemistry on coupling. This is the Corey-House reaction. In this section, we will use acid derivatives as our source substrate to compare the difference between Grignards and organolithiates, which are harsh carbon donors, to Gillman reagent, which is a mild species. Demonstrate the differences by looking at the mechanism of the Grignard versus the Gillmans using esters or acyl halides. Notice that this mechanism occurs in the case of the Grignard in 4 steps. We first have this harsh nucleophile attacking the electrophilic center of our carbon. This will realize our tetrahedral intermediate, which is an alkoxide. But because we have this really good leaving group in the methoxy, then our alkoxide will collapse to regenerate the carbonyl group. This carbonyl compound is a ketone, and it is susceptible to attack by another mole of Grignard. So attack of that Grignard will realize this tertiary carbon, which we can quench out with some acid to realize a tertiary alcohol. In fact, you will know that this is a product of the synthesis of a Grignard with an ester because of the fact that the 2 R groups are same. In contrast, we simply see that the Gillman reagent will generate the ketone because the reaction only occurs once. Note, we have attack of the nucleophile, first step. In the second step, we have collapse of the alkoxide with ejection of the halide leaving group. Note, we end with the ketone. The reaction does not proceed any further. In fact, Gillman reagents are so mild that they do not react with esters. And here is a classic example. We have a Corey-House coupling in the presence of an ester because the Gillman reagent tolerates a number of functional groups, including ketones, esters, and amides. Here you can see that we have a choice of 2 electrophilic centers, and of course the coupling took place at the halide and not at the carbon center of the ester. So this question arises, which procedure would be ideal in the synthesis of the following compound? And what I want you to do now is to pause right here, work on this problem set, and then when you get back, we'll work on it together. Excellent. What you notice is that, for example, in the reaction with sodium hydroxide, the hydroxide would react with both the electrophilic carbon of the bromine in a substitution reaction as well as that elimination, plus it will also react with the carbon center of the carbonyl. Grignard would substitute this species and create havoc as well at this electrophilic center to give you some type of alkoxide. With Lindlar catalyst, you would convert this into an alkene in C, and so the remaining solution is that of the Gillmans with our halide substituted at the alpha carbon of the ketone. And of course, the Gillman is sterile to the carbonyl, and so the coupling, which is the Corey-House coupling, will occur at this carbon center. So your answer is A. Here is another problem. It's asked which one of these products will result from the reaction of the compound on the left with the Gillman. Again, I want you to pause right here, work on the problem, and then we'll work on it together when you get back. Excellent. What you've noticed is that we have both a ketone and an acyl chloride in the molecule. We know that Gillman's does not react with ketones, but it will react with the acyl chloride, but it will go in only once. So therefore, our answer should be B. In contrast, we have this Grignard reacting with this compound. And if you notice, on the left we have an ester, and on the right we have a ketone. But remind yourself that the Grignard is a harsh reagent. So I want you to pause, work on this problem set, and then we'll work on it together when you get back. Excellent. So what you should have realized is that with the ester, the Grignard will go in twice to give you a tertiary alcohol. The only solution, therefore, will be D, because there's a tertiary alcohol on the left and will react with the ketone on the right to give us another tertiary alcohol. So our answer there is D. Herein we'll look at the MichaelAddition, i.e. the conjugate addition. Now, we'll see a contrast between the Grignard and the Gillmans with a nucleophilic addition to an enone. Remind yourself that the enone itself has two resonance structures associated with it. This one, you can see that there is a positive charge on the beta carbon. In the second one, there is the one that we're quite used to, where there is a positive charge on the carbon of the carbonyl. It is telling you that there are two electrophilic centers on the enone. When we do have a harsh Grignard reacting with the carbon, with this enone, it attacks the carbon of the carbonyl in what's called a 1,2 addition, assuming that oxygen is carbon 1 and the carbon of that carbonyl is carbon 2. In contrast, the Gillman reacts at the beta carbon because it's more mild. Enolates also generally attacks at this beta position in what we now know as a 1,4 addition or conjugate addition, i.e. the Michael addition. Another important reaction is the asymmetric reaction in which a carbonide adds to an alkene or an alkyne to form a cyclopropane. The carbene is generated by using zinc copper with methylene iodide. with an alkene, you can see that we generate this cyclopropane ring. Notice that we have retained stereochemistry that was present in the original alkene. So herein, for example, look at the placing of R1, R2, R3, and R4. Mechanism is usually shown with a carbene donating and accepting electrons in a concerted one-step mechanism. Why? Apparent, when we look at this Simmons Smith, that with the molecular orbital treatise, it becomes quite clear because we're talking about a singlet carbene. Now, this is the species responsible for the reaction of the cycloaddition of the carbene to the alkene. This cycloaddition reaction, of course, is a pericyclic reaction. And in this case, we have a empty p orbital on the carbene, which is the LUMO of the carbene. And that interacts with a field HOMO of the alkene, which is the Psi1 of the alkene. Note, we also have here a 2 orb with the lone pair, and that's the HOMO of the carbene. And that reacts with the empty LUMO of the alkene. This empty LUMO, of course, is Psi2 of the alkene. That mechanism explains exactly why we retain this stereochemistry. Because if you notice, it is syn addition to the alkene. And so herein, for example, we see cis-2-butene. And when we do have the addition of the carbene, we end up with the 2 methyls being cis on the ring. The same with the trans species, we end up with a trans arrangement of those 2 groups on the ring. So in this lecture, we did enjoy reviewing a number of coupling reactions. In the next lecture, with the carbon-carbon coupling reactions, we'll be looking at palladium catalyzed reactions, and also will include olefin metathesis with the Schrock and Grubbs catalysts. Hopefully you enjoyed this. So if you did enjoy this, please like and subscribe, and we'll see you then.